Yeah.
Okay, cool. Thank you. All right, so if there are no questions, let's go ahead and get started with our 6.2, okay? Quality of the writing, not gonna be so great today, but again, we'll try and make this work the best we can. And I'm gonna go ahead and share that screen. All right, so we have 6.2 volume by slicing. And so what I wanted us to start off with today is this sort of rooting our idea of what we've been studying when we talk about integrals. And so with integrals, yeah, there's a process, right? There's a power rule, there's the U substitution, there's these different rules. But at the end of the day, no matter how complicated things get, when we integrate a function, what we're ending up with is area. And whether we do that with dx or we do that with dy, what we're finding at the end represents the area between certain x values or certain y values. Now, what's going to be new in 6.2 as well as 6.3, okay, is that we're going to start talking about not just like one dimension to two dimension, like length is one dimension, area is two dimension, but we're going to take that a step further. And we're going to take a look at when we integrate area, so area is two dimension, we actually end up with volume. And similarly, if we integrate the area dy, okay, we're still going to end up with volume. So what's happening here is that we're going from, if we integrate one dimension, we're going to end up with two dimensions, okay? But if we integrate two dimensions, we end up with 3D shapes, 3 dimensions. All right, so that's really where I want us to be focusing our thinking, okay? We're gonna learn some processes, but at the end of the day, what we're doing is when we integrate area, we're finding volume. All right, so we're gonna take a look at these 6 pictures, all right, just to start. And so this part is volume by known cross sections, okay, volume by known cross sections. And so I'd like you to take a look at these 6 pictures, and we're gonna talk through the first one together, and then I'd like you to take a few moments to see if you can write down a description for the other few shapes, okay? So we're gonna take a look at the green one first, number 1. So when I look at this green one, I see sort of a half sphere or a hemisphere, okay? So a sphere is like a ball, okay? It's 3 dimension. It's not a circle. It could be made up of circles, but it's not a circle. A circle is flat, whereas a ball is round and it has volume inside of it. And so when I look at this green shape, one thing that I want to write down about that is that it is made up of semicircle cross sections. So for example, this right here is one semicircle. And I'm just going to take a sampling here. This is not every semicircle, but another semicircle is going to be right here. And then another semicircle is going to be right here. And in between the semicircles that I've highlighted, there are an infinite number of slices, and every single slice is a semicircle. Okay. What is the area formula for a semicircle?
One half pi r squared.
Yeah, 1/2 pi r squared. So let's say maybe like pi over 2 r squared, or we could say 1/2 pi r squared. Okay. All right. So what I'd like you to do is take a moment and look at the blue shape, the blue purple one next to the green one. And I'd like you to think about what shape those cross sections are and what equation you think we could use for the area of each cross section. Okay, so take a moment, look at picture number 2 or the blue one, and see if you can think about a name for the cross section shape as well as a formula for that cross section. Oh, Lindsay, I just got all of your requests. I'm so sorry that that was not working for you.
Sorry, I sent so many. I didn't
No,
know.
no, it's fine. It's fine. I'm glad someone told me and I wasn't just, out here unaware of that issue. So thank you. All right. Anybody have a name for this blue purple shape?
Quarter circle?
Yeah, these are quarter circles. So let's go ahead and write that here, that we have a quarter. By the way, those of you with tablets, if you have any stylus recommendations for me, I'm obviously in the market for one, so feel free to let me know at the end of class. All right, what about an area formula for the quarter circle?
Instead of pi over 2, maybe pi over 4 r squared?
Yeah, exactly. So let's maybe squeeze this in up here, pi over 4 r squared. Or we could say 1/4 pi r squared. That would also be accurate. Okay. No. Nope. Okay. So let's take a look at this yellow one over here. Okay. Take a look at this. What shape do we think the cross sections are? And what might be an area formula for that shape? Don't be shy if you think you know what this looks like.
Well, it looks like it has squares.
What tells you that they're squares?
Or rectangles.
Okay.
I don't know, just what it looks like from the side there.
Yeah, I would say in this case, I would understand if we said a square, but we don't maybe know for sure that all the sides are the same. So maybe a safer thing to call it is a rectangle because they have very similar area formulas and we can kind of cover both bases by calling it a rectangle, okay?
Gotcha.
Area formula for a rectangle, we have length times width, okay? All right, so we've seen a semicircle, we've seen a quarter circle, we've seen a rectangle. And let's go ahead and take a look at these last three shapes on the bottom, okay? So how about number 4? And what I'd like you to do actually is take a moment and look at number 4 and number 5. And I want you to be as specific as you can about what type of shape you see, okay? Because 4 and 5 are different. And so I want us to make sure we know how to tell the difference between those two shapes. All right, so what ideas do we have about how we can distinguish 4 from 5?
Is 4 a bunch of right triangles?
Yeah, I would say that 4 is going to be right triangles, okay? So yeah, 4 and 5 are both triangles. And in fact, if you already saw number 6, 6 is also a triangle, but we want to be really specific about our language. So these are right triangles, and that means that I can find the area by saying 1/2 base times height, but the height is already here as part of it, and then the base is along the bottom, okay? How would we describe number 5? I think it's maybe hard to distinguish between 5 and 6, but I think maybe one thing we could all agree on is that the height for these triangles is really going to be like here, rather than one of the sides of the triangle. Okay, so even in the red one, the height of the triangle is going to be like here. Okay, so we can use the formulas of 1/2 base times height. We can still use those formulas, but we'd have to figure out a way to find the height in our rectangle. So 5 and 6 would be a little bit more work than maybe number 4, okay? So let's sort of zoom back in for a moment. Take a look at these pictures, okay? Now, I know it sounds silly, but I think it's worth spending time practicing looking at pictures and being able to describe the shape. And I can tell you that this is one of those things. Is there anybody in here who was like really good at learning their multiplication tables? Like it was just really easy for you and you just got it? Okay.
Only some numbers because I know songs.
Okay. I think for me, like multiplication tables when I was little, for some reason, was really easy, right? And so it was one of those things that I was kind of like, oh, this is easy for me. But then I had classmates where it wasn't easy for them and they really struggled with it. But it seemed to be like one of the first times there was kind of a divide in the learning. Like people either got multiplication and that meant they were good at math, or they didn't get their multiplication tables and that kind of meant that they were bad at math. Or at least that's how they felt, or maybe were made to feel. And I think that what we're about to look at, all of this volume stuff, some of us are sitting here looking at the pictures being like, oh yeah, I totally see that. And it comes naturally for you. And you might be the kind of folks who spent a lot of time maybe building things or tinkering with things. And maybe that's how you've sort of developed these skill sets, or maybe you're just really good at it, okay? But there's gonna be a subset of this class who is looking at these pictures at their computers at home right now being like, what in the heck are these shapes? And like feeling very overwhelmed about now we're moving into like a 3D place, okay? So I did want to let you know that as good as I was at multiplication tables, the first time I saw this stuff and the second time I saw it, so I saw it in high school because I took calculus in high school. I saw it in college because I took Calc 2. And then I was like, well, this will just go away by the time I get to Calc 3. Turns out I was super wrong. And I never really learned it until I got to Calc 3. And then I was like, oh, I can learn this. I just have to really practice visualizing things, okay? So as we're going through these lessons, please know that I've spent my fair share of years feeling like I would look at these pictures and just be like, I don't really understand how she got the formula from there. So if you were feeling that way, I have 100% been in your shoes. And if you're looking at these being like, oh yeah, I totally get it. I was never that kid, so good for you. I don't want to take away from that, but I think it is one of those things you just kind of gotta practice looking at pictures, okay? So that being said, let's go ahead and move on to some practice questions, okay? So in this section that we're gonna do right now, you'll notice that we don't really have any pictures, and that's kind of on purpose, okay? I want us to be able to work with pictures, but also draw our own pictures. However, when you go to the practice questions on Canvas, all of those have pictures, okay? So make sure that you know how to generate these pictures, because that's definitely going to be helpful when you get to not just the final exam, but Calc 2 and Calc 3, okay? So let's take a look at example 1. Example 1 says, the base of a solid S is the region of the plane bounded by the parabolas f of x equals x squared minus 3 and g of x equals 5 minus x squared. Cross sections perpendicular to the x-axis are squares. Find the volume of the solid, okay? So to me, the key word in here is that I'm finding the volume of a solid. And so as soon as I see the word volume, I'm already thinking volume equals the integral of area dx, or, that's not what I wanted to write, or it equals the integral of the area dy. Okay, so as soon as I see that word volume in the question, that's what I'm thinking in my head already. Now, what we're going to do is we're going to start by sketching this diagram. And our diagram is going to include this parabola, f of x equals x squared minus 3, and this one, g of x equals 5 minus x squared. So okay. So x squared minus 3, as we know from last week, is a parabola that is facing up, and the vertex got moved down 3 units. And so I'm going to just sketch this parabola like this. No, come back. Like this. Okay. Now, when we look at our g of x parabola, I know that it's a parabola, but I know that it's upside down because of the minus, and the vertex has been moved up 5 units. Okay. So what the area that I'm looking at is the area between the orange parabola and the pink parabola, okay? This second sentence is really helpful for me to draw those lines. So if you think back to last Thursday's lesson, we would have like a curve and another curve, and then I would draw lines like that represented the rectangles. So we're going to be drawing lines now, but the lines are going to represent something different because we're looking at 3-dimension, not 2-dimension, okay? So this second sentence says that the cross sections perpendicular to the x-axis are squares. What that means is I do not want to draw my line this way, because that line is not perpendicular to the x-axis. So I'm going to undo that, and instead I'm going to draw some lines that are perpendicular to the x-axis. So for example, this could be one line that is perpendicular to the x-axis. Another example could be like this one over here. Okay, now when I draw these, this is not like LRAM or RRAM where it needs to be evenly spaced out. And if I only draw 2, that doesn't mean there's only 2. I'm just using this to help me think about which direction the lines are, okay? So I'm gonna draw a few more in here just so we can kind of see, but this would be a line perpendicular to the x-axis, and so with this one, okay? Now these lines that I drew, okay, each one of these blue lines, what does that represent? Well, it represents the bottom of a square. So if I imagine a square sticking straight up out of my tablet, or for you guys, straight out of your computer, what's coming out of that is a square. And this line would be like this part, okay? If I scroll back up for a moment, I want us to go back and look at the one with the rectangle, okay? So kind of keep this in your mind, but let's look at the one with the rectangles. So do you see how this has like all the rectangles coming out? That's what we were focusing on last time. But what we didn't really talk about was this part. And I'm going to circle this in the pink. Okay. That pink is the base. So that pink space is like the space between my pink parabola and my orange parabola. And then from that, all of the squares or rectangles are coming out of the shape. Okay, so let's look back at this diagram again. I would have a lot of squares coming straight out of my screen, okay? Now, I want to ask us a few questions, okay? If I had a square, if I marked the square right here at that very far left, would you say that that square is smaller or bigger than most of the other squares inside that shape?
Smaller?
Smaller, okay, how do you know that?
Just because the line that's perpendicular is a lot smaller than the rest of the ones that are inside of the area.
Yeah, exactly. Like this little blue line is so much shorter. And it's even shorter than this green one that I drew over here. So that if I were to draw a square representing like the one that's coming out of that blue line, it would be pretty small. And then where would I find the biggest square that's coming out of this base?
Towards the middle.
Yeah, at the middle, right? The middle one would be the biggest. In fact, the one that is right on the y-axis would be the biggest square out of all of them. So if we think about starting from the left and moving to the right in our shape, we could say that our squares start small, that they get progressively larger. And then for this particular graph, at halfway, they start to get smaller again. So small square, slightly bigger, biggest square in the middle, and then everything starts to get smaller again after we cross the y-axis. Okay. So what our goal is here is to find the volume of the solid. Okay. And so we wrote down our formulas earlier. Now, I've been asking you guys to make a lot of decisions about should we choose dx or dy, and you guys have done so well with that. And I'm wondering in this case, does anyone have a gut instinct about whether we should choose dx or dy?
dx.
What makes you say dx?
Because it's perpendicular to the x-axis.
Yeah, because it's perpendicular to that x-axis, okay? So I would say that that is 100% correct in this case, all right? So we're gonna go ahead and say that we're using this first formula where we're gonna set it up dx. Now, one thing I want us to start thinking about is, yes, it's perpendicular to the x-axis, but another way to think of this is we are stacking our squares along the x-axis, okay? I don't know how many of you remember when you were a little kid, or if you have younger siblings or cousins, or even your own kids. But when I was little, there was a toy that was like, it had like 6 plastic rings, and like there was like the big one was like the red one at the bottom, and then there was an orange one and a yellow one and a green and a blue and a purple, and they got kind of smaller and smaller as they went up. Anybody remember that toy?
Yep.
So if we think about that toy, the way that toy is built, we would use dy to figure out a volume because we are stacking our circles up the y-axis. So what we have in this case is we actually almost have it like we took that toy and we turned it horizontally. Then we're stacking ours, and we had squares instead of circles, and we're stacking those squares along the x-axis. So whatever direction you're stacking along, that tells you if you want dx or dy, okay? All right, so now let's get into our formula. Whoa. So we have volume equals the integral of the area dx, okay? Now, what is the area formula for a square? Length times width. Length times width, yes, okay. So I'm gonna rewrite my equation, but I'm gonna have the integral of length times width dx, okay? And so what I'm saying, and this is based off of what you told me, is that the area of the shape I'm interested in, the square, is length times width, okay? If I said that the cross sections were semicircles, instead of saying length times width, you guys would put 1/2 pi r squared. But if I said the cross sections are quarter circles, wherever I have length times width here, you would put 1/4 pi r squared. And if I said the cross sections are rectangles, would that change what we have, or would it keep it the same?
Keep it the same.
Yeah, if we had rectangles, we would keep it the same, right? So the only difference with the square and the rectangles, the square is like a special case. It's so special because the length is equal to the width for the square, okay? So let's go back and look at our diagram for a moment. Oh, okay. So when we look at our diagram, the blue lines that I drew, we can say that those represent the length of the square, okay? Or we can say that that is the length of the square. All right. Now, that length is something that I can find if I think back to Thursday's lesson. So the length of the green line in my diagram is going to be my orange curve minus my pink curve. Okay. We can think about that as our case when we said, oh, we just do top minus bottom. Top minus bottom gave us the length of one specific segment. And so what we're going to do here is, instead of writing length in words, I'm going to write it as 5 minus x squared, that's the top curve, minus x squared minus 3, because that's the bottom curve. So what I mean by that is I will say the integral of 5 minus x squared, okay, minus x squared minus 3. And that together will give me the length. How can we represent the width of this particular square?
Same.
Same thing, right? So I'm going to go ahead and write that again. 5 minus x squared minus x squared minus 3. And I'm going to sneak in a dx at the end, okay? So the first one represents the length, and the second thing, that represents the width. And again, we can say that they're the same because it's a square. All right, so let's clean this up a little bit. Inside of the first brackets, I'm going to get 5 minus negative 3, which is 8, minus 2x squared. Okay, so this is again my length. And then my width will simplify to be the same thing. Okay, so I've got my length times my width. Now, there are a few things I need to do before I can actually calculate an answer. One of those would be, it's probably a good idea to simplify that, meaning I should probably FOIL that. That would make my life easier, okay? But what other information do we need to know in order to find this volume?
Maybe the intervals, the A and B?
Yeah, exactly. That's what we need, because right now we are missing a number down here and we're missing a number up here. So how do we know what numbers to plug in? Okay, when we look at volume, we're going to want a specific number as our answer. So it is important that we have those bounds. All right. So let's go ahead and FOIL first. All right, I think that's something that we can all handle. So 8 times 8 is going to give me 64 minus 16x squared minus another 16x squared is minus 32x squared, and then 2x squared times 2x squared is plus 4x to the 4. Okay, so that's just foiling out our answer. Now let's also think back to Thursday's lesson. Sometimes in the area problems, they tell us where to start and stop. But in the cases where they don't, what was our strategy to find our A's and B's?
Setting the equations equal.
Yeah, we're going to set that pink equation equal to the orange equation. Okay, that's awesome. So a lot of these skills that we learn, it's like we learn them, but they don't just apply to one particular problem. They apply to a lot of different problems. Okay, so let's take some time now to find our A and B. So we have x squared minus 3 equals 5 minus x squared. So I'm going to add the x squared to the other side, and I'm going to add the 3. And so I'm going to get x squared equals 4. How many answers should I get?
2.
Perfect. X equals a positive 2 or a negative 2. Okay, so with that one equation, now we can go ahead and find our A and our B. So our A is going to be negative 2 and our B is going to be positive 2. Okay, so I'm going to come back to my equation. I'm going to put a negative 2 at the bottom and I'm going to put a positive 2 on the top. All right, now if I were doing this problem like regularly, at this point I would probably decide to use the idea of symmetry. I would change my bottom bound to 0 and I would just double my final answer. Okay, is that something folks feel comfortable doing, or would we prefer to just solve the integral that we have right here?
I prefer to solve.
Okay, let's do it then. So I'm going to go ahead and take the antiderivative of each one. So I don't need my integral symbol anymore, okay? The integral of 64 is going to be 64x minus 32 over 3x cubed plus 4 over 5x to the 5th. And then I'm going to draw the line and put a 2 and a negative 2. Okay. So now let's go ahead and plug in our 2, and then we're going to plug in our negative 2. So we've got 64 times 2 minus 32 over 3 times 2 cubed plus 4 over 5 times 2 to the 5th. That's my first term. Minus plugging in negative 2. So 64 times negative 2 minus 32 over 3 times negative 2 cubed plus 4 over 5 times negative 2 to the 5th. Okay. So now this is actually probably a really good chance to practice that, like simplifying by grouping, meaning like I could combine this one with this one, but then because this is going to be a fraction over 3, I can combine that with this fraction over 3. And then this is going to be a fraction over 5, and I can combine it with this fraction over 5. All right, so let's simplify and see what we get. 64 times 2 is 128 minus 32 times 8. Let's see what that gives us. 256. So I get 256 over 8 plus 2 to the 5th is 32 times 4 is 128 over 5. Okay, so that's the first bracket. Minus a negative 128, so that'll be plus 128. And this is going to be minus 256 over 8. And this will be a plus 128 over 5. And so now I'm going to combine my 128s. That'll give me 256. So again, that was this plus this gave me this. And then this will give me minus 512 over 8. And that's because I combined this one with this one. And then last but not least, I'm going to combine the 128 over 5 with this 128 over 5, which is going to give me plus 256 over 5. Okay. And now I'm going to turn them all into something with a common denominator, and smallest common denominator here I think is going to be 40.
Why is it over 8 and not over 3?
Because I've had a really long morning. I'm really glad you caught that before we started doing that.
Okay, thank you.
Okay. I think I meant to write a 3 and then it turned into an 8 and then I just kept going.
Yeah, it looked like
Much
it.
nicer common denominator. We'll go with the common denominator of 15. I like that.
There we go.
Okay, thank you. All right, so this is going to give me 3840 256 60 and 768, I think. Yeah, and I don't think that reduces, so I think that is our final answer. Are other folks getting this answer? Yeah, I think that's right. Okay, so here is our worked out problem for what happens when I take two parabolas, I take the region in between them, and I say from this region, I'm going to be having squares come out of the paper or out of the screen. And each of those squares, if I add up the area of every single square, I will get the volume of the overall shape. Okay. What kind of questions do we have so far? How are folks doing?
When you talked about the step of symmetry, how would that work? Like, what's the
setup for the symmetry?
Yeah.
Okay, good question. So if I were to use symmetry, then maybe let's say at this point, okay, what I would have done is changed it to be 2 times the integral from 0 to 2 of the same thing.
Okay, that makes sense.
Yeah. And for me, what works out with that is I feel like I don't always trust my calculations with so many negative signs, right? Like I can't even make a 3 and stay a 3 the whole time. Sometimes the 3 becomes an 8. So like the signs can be sometimes really tricky and it's just not where my brain is at. So if I think about if I plug 0 into here, what would happen to that whole second bracket?
Turn into 0.
Yeah, it would turn into 0, right? So what I would end up getting is I would end up with this first part, and then I would just double my answer. So take that for what you will. I think both versions are definitely viable options. I think there's nothing wrong with saying I just want to do the formula the way it's written because this is already so much for my brain. And it's okay to be like, but I know I'm not so good at these other things, or maybe I think it's faster, so I'm just going to do symmetry, okay? What other questions do we have?
I guess I'm a little confused on how you got the length and width by subtracting one from the other.
Okay. So let me maybe zoom into that. Nope, sorry. Okay. So let's talk about that down here, okay? So if I were to draw a picture of that diagram again, but this time maybe put some numbers on it. Pink and then orange, okay. Nope. So I knew that this parabola, it crossed the y-axis at 0, -3. And the other parabola, I know that it crossed the x-axis at 0, 5. So maybe one question that I could ask is, how long is the distance between the vertex of the orange parabola and the vertex of the pink parabola?
8.
8. How did you get that?
5 plus 3.
Okay. But maybe another way you could have thought about that is 5 minus -3.
Yeah.
Yeah, right? Okay. So let's think about, let me just write some arbitrary points, okay? So let's say that this point had a y value of 4, okay? And let's say that the point on the pink parabola directly underneath that had a y value of -1. How far apart are those 2 points?
5.
5. And you can get that by doing 4 plus 1, or you can think about it as 4 minus -1.
Mhm.
And so these are just some random whole numbers, right? But I could pick some other points that maybe were decimals, but it would still be, in order to find the distance between those 2 points, I would take the y value of the top curve and I would subtract the y value of the bottom curve. And so what that does is it gives me the length of that line. Now, in this case, the length of this line represented the length of the square. And so because I know the length of the square is going to be top curve minus the bottom one, instead of writing like every single number it possibly could be, I wrote it as an equation so that when I plug in my numbers, it will automatically give me the numbers for every single square in there.
Okay.
Okay. I think that question right there, though, pretty much is one of the hardest things to see, because I think we're used to working on geometry like by itself and dealing with like algebra by itself, and now we're really intermixing the two of those. We have to be able to represent a length or a width or a radius using equations, okay? So that's why I think the diagram is really helpful, because it sort of breaks up the steps. Like, can I draw the picture? Help me pick dx or dy, and then what does that line represent? Okay, and the problem will always tell you what it represents. Other questions? These are really good questions, folks.
How do you solve problems like this if it doesn't tell you what shapes are in the cross sections?
So if it's a cross-section problem, like this first half of the lesson, then they will always tell you what shape it is.
Okay.
Okay. In the second half of the lesson, we're going to zero in on a very specific kind of cross-section. And in those cases, you won't be told, but the way the problem's written, you'll know what that shape is going to be.
Okay, thank you.
All right, so let's do this. Let's do one more problem just to kind of practice it a little bit more. And then we're going to go ahead and take a break. All right, so let's take a look at example number 2. Okay, so example number 2 says compute the volume. All right, so already I'm like, okay, I'm going to need to find volume. And so even before I read further, I might want to write down volume equals the integral of area dx or the integral of area dy. Okay. And then I keep reading. So I'm finding the volume of the solid whose base is the region between f of x equals 4 minus x squared, that's one curve, and the x-axis, so that's the other curve, okay? Now, these cross sections are going to be perpendicular to the y-axis. All right, so they're perpendicular to the y-axis, and these are not squares like in example number 1, but they are going to be right isosceles triangles. So what does a right isosceles triangle have that's special about it? I mean, I know all triangles have 3 sides, but what's special about a right isosceles triangle?
It has 2 right triangles that are identical.
Yeah. So if we sort of scroll back up for a moment, okay, so keep in mind this word right isosceles triangle, and I'm going to scroll back to that set of pictures that we had at the beginning, okay? And let's look at example 4. This is kind of what our shape is going to look like. We're going to have some triangles that are smaller than others. We'll have bigger triangles, but every triangle will have the base and the height will be equal to each other. Okay? Now, this line down here is going to be like this line that I drew in the previous problem. Okay? But in question number 1, that line represented the length of the square. In question number 2, what is that line going to represent?
The base.
Yeah, the base of the triangle. And that's actually going to be the same as the height of the triangle. Okay? So let's go back to example 2. All right, we're going to draw a diagram. I know that 4 minus x squared is an upside down parabola with a vertex at 0, 4. I know that the x-axis is the like the other part of that region, okay? So I'm looking for lines that are perpendicular to the y-axis. So if I draw one like this, because that's what I did in the previous problem, I'm not correct. Because in the previous problem, it said perpendicular to the x-axis. That's why we drew them that way. But in this case, it says perpendicular to the y-axis. So I need to read really carefully. So I'm going to erase this line. And instead, I'm going to draw a line that goes this way. And that line would represent the base of my right isosceles triangle. Okay. Now, again, I can draw as many bases as I want to help me get an idea of what things look like. But if I drew a base up here, I would know that that triangle is going to be smaller than the first one I drew. If I drew a base here, I would know that that triangle is in the middle, size-wise, of the other triangles I've drawn so far. And if I went all the way down to the bottom of the region, that triangle, based on this picture, is going to be the biggest one out of all of the triangles. Okay? So let's decide dx or dy, and then we'll set up our integral. Okay? So what are our thoughts here? Area dx or area dy? dy, yeah, because we are stacking our triangles up the y-axis. So this is actually like that toy we were talking about earlier that had like the red ring at the bottom and the purple ring at the top. It's going vertically or up the y-axis, and so we have to say that we're going to be using everything with respect to y. So let's set up our integral. So our volume equals the integral of the area of a right isosceles triangle. Okay, so I can write area here, dy. And I'm going to be even more specific. I'm going to say, instead of area, I'm going to write 1/2 base times height. Okay. And the reason why I'm writing 1/2 base times height is because that is the formula for a right isosceles triangle. And if they said square like they did last time, I would be wrong to use this formula. Or if they said, hey, the cross sections are semicircles, it would be wrong if I use this formula. But the reason why I'm writing this formula is because of the shape that they tell me, right isosceles triangle. Okay. Now, I bet we can fill in our bounds right now. I'm not sure that we need to do this one algebraically. Does anybody think they know what the bounds are?
Plus or minus 2?
Hmm.
Oh, wait, no.
I think I know where you got those numbers. Did you get them from here and here?
Yeah, and then I got it from the f of x function.
Yeah, okay. But we're stacking them up the y-axis, right? So I think that's where you started to catch yourself. We want to make sure that we use y values for these bounds. So what's the smallest y value in the region we're looking at?
0.
0, yeah, because it's right on the x-axis. And so I can put a 0 in for my a, and the vertex, that y value tells me where I'm going to stop. So 4. Okay. So remember, if we're shifting our perspective to be a vertical one, we need to think about what our bounds are going this way, from smallest to biggest. All right. Now let's think about the base. Okay. So each of these green lines represents a base. Now, if I wanted to find the length of a line, okay, like we talked about sort of again at the end of question number 1, we were able to do top minus bottom. But when we think about what we learned about finding area that's kind of sideways or dy, we didn't do top minus bottom, we did right minus left. Now, in this case, the right curve is this one. It's the parabola. But the left curve is also the parabola. Okay? And that causes us to have a little bit of a problem. So what we're going to need to do is we are going to need to use the idea of symmetry a little bit here. Okay, so what we're going to do is we're going to find the distance from here to here. Okay, so half of that distance. If I find half of that distance, then in order to put in my number for the base, I'm just going to double it. Does that strategy make sense to folks?
Yes.
Yeah, okay. So if I only look at this little yellow region right here, okay, what's the right curve for that region?
The parabola.
The parabola, okay. So the right curve is our parabola. what is the left curve for the yellow line?
The y-axis.
The y-axis, good. So that is going to be x equals 0. Okay, that's another name for the y-axis. So what I need to do is my parabola is currently written like 4 minus x squared. But what I want to do, what I want to do is scroll up the page. Okay, so what I want to do though, this is what y equals. But if I want to have an equation with a dy and my bounds are y values, my equation needs to be in terms of y. So right now I need to get rid of, or not get rid of, but I need to isolate the x so that I can have my equation in terms of y. So I'm going to go ahead and subtract the y to this side and add the x squared to the other side. And then I'm going to solve for x by taking the square root of both sides. Okay. Now my right minus left will be right minus left. That will give me this distance right here. So half of the base. So half of the base is equal to the square root of 4 minus y minus 0. And you don't have to write that minus 0. But that means then that the whole base is going to be 2 times the square root of 4 minus y. Right? If half the base is the square root of 4 minus y, then the whole base is 2 times the square root of 4 minus y. So what I have here now, this, okay, that is this whole part. So now that we have an equation for the base, I can put that in to this equation for the base. And the nice thing about that, even though that was quite a bit of work, it's a right isosceles triangle, so I can put that same thing in for the height. All right? So that means that I have the integral from 0 to 4 of 1/2 times 2 square root of 4 minus y times 2 square root of 4 minus y. Okay. So I just want you to look at that for a moment. Take a while to make a little bit to make sure that what we filled in so far makes sense. Okay. Are there any questions so far about where things came from, why we're able to plug certain things in certain places?
We were solving for the base. Why did we get things in terms of y again?
That's a really good question. So the reason we had to rename it was for this, okay? When we decided that it was going to be dy, we also decided that the bounds were going to be y values and that we should have y's in the equation, not x's.
Okay, that makes sense. Thank you.
All right.
How did we get the height as the same as the base again?
Great question. So we got that because we have a very special kind of triangle. We have an isosceles right triangle. And what that means is that it's a right triangle, but it also means that the base is equal to the height.
Oh, okay. Thank you.
Okay. Mhm. Okay. So this, I would say, is where most of the work is, all right? This is where most of the work is, making sure that you come up with exactly the right formula and that you've been able to craft a diagram that sort of matches your reasoning, all right? Now, from here, in theory, the integral itself shouldn't be as hard as some of the ones we saw in chapter 5. All right, you'll notice that a lot of power rule comes up, but it's not going to be a ton of like exponential and log questions. It's going to be more basic ones like power rule. All right, so let's see what happens here if I try and simplify this. So I'm going to gather some like terms first. I notice that like this 1/2 and this 2 and this 2, those are all constants. So I'm going to bring those all out to the front. And 1/2 times 2 is 1, times 2 will give me 2. So now I have a 2 in the front. And then the integral from 0 to 4. And let's see what we have left. Okay. Now, at first, when we were setting this up, I don't know if you guys were getting nervous. You're like, oh no, a square root. I was also getting a little nervous. However, one of the things is that, you know, sometimes it's going to be a little bit messy, but oftentimes it cleans itself up. And here's a really good case for that. When I have the square root of something times the square root of itself, I can actually simplify that just to be the thing underneath the square root. Okay. Now I think this integral looks way more manageable. All right, so when I integrate, I'm going to have that 2 in the front. I'm going to get 4y minus y squared. And I'm going to plug in 4, and I'm going to plug in 0. Okay.
Where did you get the 2y?
Oh God, what is happening in my brain? Thank you for catching this before I posted this like forever, and it's archived forever in the internet. Okay. 4 minus y, so that's 4y minus 1/2 y squared. There we go.
Teaching everyone wrong math.
Okay. So now we can plug in the numbers. Is this the integral that everyone's getting, by the way?
Yeah.
Yeah, okay, cool. So I'm actually gonna distribute this to, and here's my reasoning. I know I don't normally distribute, but I see this fraction here, and I realize that if I distribute, that fraction's gonna go away. So I'm gonna distribute so I don't have to work with the fraction. And that will give me 8y minus y squared, plugging in 4, plugging in 0. So 8 times 4 minus 4 squared minus 0 is going to give me 32 minus 16, which gives me 16. Whew, I'm so glad you caught that 2y. We would not have gotten the right answer, and I would have been like, why not? Okay. So, thoughts, questions. How are the brains feeling?
Feels like I'm gonna need a lot of practice.
Well, good thing there's like 6 practice problems on the canvas for you. Okay, let's take a break. So it's 11:05 right now. If we can take a 7-minute break and be back here at 11:12, that would be excellent. All right, so we'll meet back here at 11:12. We'll go over a few more examples and kind of see where that takes us for today. Okay, we might have a chance to start a little bit of Thursday's main topic just to kind of get us thinking about it. But if we don't, that's also okay. All right, so I'll see you back here in 7 minutes. All right, so before break, we took a look at this idea of volume. And what we had been doing previously was that integrals was one way to go from 1 dimension to 2 dimension. But what we can do is do integrals that will help us find 2D to 3D. Okay, and if you're thinking, all right, I'm gonna make it all the way through Calc 3, you spend a lot of time working in 3 dimension. So it's basically a lot of what we do in Calc 1, but in 3 dimensions. And so this is a good chance to just kind of start to learn how to visualize different kinds of graphs. And so we took a look at some pictures that were pretty common cross sections, I would say. Semicircles, quarter circles, rectangles or squares, triangles come up a lot, okay? But really, in theory, you could have any shape as long as that shape is consistently the same shape, maybe not the same size, but the same shape all the way. Then what you can do is use this idea of volume equals the integral of area in order to find the volume of that shape, okay? So in question number 1, we took a look at a situation where we had 2 parabolas, we had to find the bounds, and we were able to determine the area formula for the cross-section was going to be length times width because it was a square. And then when we moved on to example 2, we realized that it was a different cross-section. And so we had to have a different equation. We had to have 1/2 base times height because it was a right isosceles triangle. And what was also different about number 2 is that we had to change all of our equations to be in y's. And the reason we did that was so that everything would match with the dy we picked at the beginning. And so now let's go ahead and take a look at question number 3. Okay. So question number 3 says a solid has a base in the form of the ellipse x squared over 25 plus y squared over 16 equals 1. Find the volume. All right, so find the volume. There it is. Find the volume if every cross section perpendicular to the x-axis is a rectangle. Okay, so we don't have a square, we have a rectangle. So let's get started with writing down our 2 volume formulas that we're going to pick from. Volume equals the integral of area dx, or the integral of area dy. So based off of the information we have in our question, what are folks thinking? dx or dy?
Dx.
It's going to be dx, yeah. And that clue is that perpendicular to the x-axis, okay? So I'm going to go ahead and circle this one. And I'm also going to cross out this one, all right? And now let's move on to our diagram. All right. So depending on your pre-calc teacher, you may or may not have gotten to conic sections, all right? Or maybe you learned about conic sections and you're like, this can't possibly come up again, but good news, folks, it comes up again. And this question actually is the kind of question that you'll see with within the context of Calc 2, okay? So we bring back conic sections quite a bit in Calc 2. So if I look at this ellipse, I know that the center is at the origin, okay? So I'm gonna go ahead and jot that in. The center's at the origin. And the number under x squared is 25. And if I take the square root of that number, I will get 5. And 5 is the number of units I'm going to count out on the horizontal direction. Similarly, let's look at the number under y squared. The number under y squared is 16. The square root of 16 is 4. So from my center, I'm going to go up and down 4. And now when I connect all 4 of these exterior points, I end up with an ellipse, okay? So let's draw in our lines that represent the cross section. I want to draw these lines so that they are perpendicular to the x-axis. So if I draw the line like this, no go. That is parallel to the x-axis. I want to make sure I draw the lines perpendicular. So like this, like this, like this, like this. You can draw as many or as few as you want, but I would recommend at least one, okay? Now, what does this line represent? Well, this line represents the base of a rectangle, okay? So if I think about a rectangle, I have the base, and is this rectangle gonna be taller than it is wide, or is it gonna be wider than it is tall?
Taller.
It's gonna be taller because this last part that I didn't read out loud says the height is 3 times the base. So whatever my base is, the height is going to be 3 times as tall, okay? So 3 times as tall. Okay, so now we need to think about our area formula. So we've got volume equals the integral of area dx. And I know that the formula for an area of a rectangle is base times height. Okay. Ooh. Okay. So in order to find the base of my rectangle, I need to find the distance between the pink curve, which is on the top, and the pink curve, which is on the bottom. Okay, so this is an issue that we've run into before, where now the top and bottom curve are the same. So let's take a look at how we handled this in problem 2. In problem 2, because my green lines went from the pink parabola to the pink parabola, my strategy was let me find half of that and then double it. And that's what we did right here. Okay? That's a pretty common strategy. So we're going to take a look at our diagram for example 3, and we're going to do something very similar. I'm going to find the height of half of it, and then I'm going to double it. So to find half of the base, all right, what's the top curve?
The ellipse equation.
Yeah, it's going to be the ellipse equation. So let's write that out. All right. And the bottom equation is going to be y equals 0. Okay. So in order to find that height, what I need to do in this ellipse equation is I need to isolate y. Okay. So I'm going to go ahead and multiply the whole equation by 400. And let's see what happens when I multiply the whole equation by 400. 400 divided by 25 is going to give me 16x squared. Plus 400 divided by 16 is going to give me 25y squared equals 400 times 1 is 400. Now I'm going to subtract the 16x squared. Now I'm going to divide by 25. And now I'm going to take the square root. All right, so I've gotten my top equation in terms of x. The reason why I wanted to get it in terms of x is because we decided it was going to be a dx equation. So what that means, what that means is that half of the base is going to be the square root of 400 minus 16x squared over 25 minus 0. That's our top minus bottom. But what that means for the whole base is it's going to be 2 times that square root. Okay, so same kind of reasoning that we saw in example number 2. Now this is what I'm going to put in that equation back up at the top for the base. So this will give me the integral of 2 times the square root of 400 minus 16x squared over 25. Now this right here is my base. It's the base of the rectangle. How do I use this to help me find the height of the rectangle?
Multiply by 3.
Multiply it by 3, exactly. So the only thing that's going to change is instead of a 2 in the front, we're going to have a 6 in the front, right? Because 2 times 3 gives us 6. Okay. So let me zoom back out for a moment. I know we talked about a lot of different strategies here. All right, give you a moment to see if there are any questions so far.
Where'd you get the 400?
So up here, I was thinking like, how could I get rid of these denominators? So I realized that if I multiplied by 400, then the denominators would go away.
Gotcha.
Yeah. And I got 400 because I did 25 times 16.
Yeah, I see it.
All right. Other questions so far?
So did you use this strategy because the base is from the parabola to an axis instead of, because I'm looking at example 1,
Mm-hmm.
the equation subtracted by another equation.
Mm-hmm.
Is that because there wasn't like an axis that was like one of the lengths?
Yeah, so if I kind of zoom in on the picture I have here, like if I think about the top and bottom curve for the whole length, for the whole base, the top curve is the same as the bottom curve. So if I just subtracted them, I would get 0.
Okay.
So I look at the picture and I'm like, I know that's not 0. I know it has a value. So I use the idea that I could take half of it and double it. And it also makes for a nice bottom in terms of like the bottom equation is just 0.
Okay.
Okay.
Thank you.
Mm-hmm. All right. We ready to try working through this integral? I think it's going to be not quite so bad, even though it looks like a lot right now. All right. I think once we take those constants out, we'll see that it's going to clean up pretty quickly. So the constants I'm going to take out are the 2 and the 6, and I'm going to bring them out to the front. So that'll be a 12 in the front. So this will give me 12 times the integral of, now I notice I have the square root of something times the square root of something. So that just gives me that something. All right. So when you're multiplying something by itself, it's not a bad thing that you have a square root in there. Okay. I'm going to bring one more constant out to the front. This divided by 25, I'm going to bring out to the front. So my front number will be 12 divided by 25. And the reason why I'm doing that is so that I don't have to deal with the fractions on the inside when I am taking my integral. All right, so like 400 minus 16x squared looks way nicer than like 400 minus 16x squared over 25. Now, the last thing I need to do is I still need to find my bounds, right? I need to find my bounds so that I know what to plug in. So let's go back to our diagram here. If I look at my bounds, what is my lower bound going to be? or my A?
-5.
-5, very good. How'd you get that?
It's from the x squared divided by 25, so it'll be like square root of 25 is 5. Yeah,
Exactly.
5.
Mm-hmm. Good. So you've actually given us both bounds. We've got a -5 down here. And we've got a +5 up here. Okay. Now this again, when I look at this, I'm like, oh, thank goodness for symmetry. Because what I could do is change the bottom bound to a 0 and then multiply the whole answer by 2 at the end. Okay. Now, I think we're going to do it just the long way this time again, just to kind of practice, all right? I don't want to add on too many layers, but if you personally feel ready to start setting that bottom bound to 0 and doubling, you're more than welcome to do that, okay? So let's focus on our antiderivative here. I've got 12 over 25. My antiderivative is going to be 400x minus 16 over 3x cubed. And I'm going to find it from 5 and -5. Those are the numbers I'm going to plug in. Okay. So I get 12 over 25, 400 times 5, minus 16 over 3, 5 cubed, minus 12 over 25, 400 times -5, minus 16 over 3 times -5 cubed. Ooh. Okay. So I have 12 over 25, and 400 times 5 gives me 2,000, right? 5 to the 3rd power times 16 is going to give me 2,000 over 3 minus 12 over 25 times -2,000, and then plus 2,000 over 3. All right. Let's see. 12 over 25 times 2,000 will give me 960 minus 12 over 25 times 2,000 divided by 3 will give me 320 plus 960 minus 320. So 960 minus 320 plus 960 minus 320 is going to give me 1280. And 1280 represents the volume. Oops, the volume. If I have the base as an ellipse, and then I draw these cross sections that are rectangles, where the height is going to be 3 times the base, and I'm going from -5 all the way to 5. So I'm filling the whole ellipse with these rectangles. All right. How we doing out there, folks? Any questions? You ready to try another example?
Do you mind repeating how we got the top and bottom bounds?
Oh, like this part here?
Just the -5 and the 5.
Oh, okay. Sorry, I misunderstood. Yeah. So when we went and we graphed our original, maybe it would have been better if we wrote down some coordinates along the way. But when we graphed it, to graph the sort of x-intercepts, I took the number under x squared, which is 25, and I took the square root. Because the ellipse formula, that number on the bottom that's being squared, that tells you how far to go side to side. So this is negative 5, 0. And this one is 5, 0.
Oh, okay.
Okay.
Thanks.
If you were stacking up the y-axis, your starting bounds, your bounds would be negative 4 to 4.
Okay, that's perfect.
Okay, cool.
I had a question real quick, actually. Could you explain again how you got the 400? Just because my computer cut out right as you were explaining that.
Oh, yeah, of course. I just wanted to get rid of the fractions. You don't have to, but I prefer not to work with fractions if I don't have to. And so I did 25 times 16.
Okay.
And that gets 400.
Mm-hmm. Okay.
And then multiplied everything by that number so that I could get rid of the fraction.
Okay, awesome. Thank you.
All right. Okay, so I looked ahead. I realized example 4 is the same as example 3. So we're, wait, is it? Yeah, so we're not going to do that one. We're going to skip to example 5, okay? All right, so example 5. Here's what I'd like to do. I'd like to give you folks in the cyberspace a few moments to determine for yourself, do you think this is dx or dy? And then I'd like you to come up with a diagram of the shape and maybe even an area formula for the cross section. Okay, so let's take about 3 minutes here and start to set up problem number 5 on our own. All right, so can I get a volunteer to tell me whether they think this is going to be dx or dy?
Dx.
It is going to be dx, and what made you choose that?
because it's perpendicular to the x-axis.
Yeah, exactly. Perpendicular to that x-axis. So we're going to say find that area dx. Good. All right. So with this problem, the problem says that the shape you have is a circle. X squared plus y squared equals 4. Okay. But in Calc 2, you might get the same problem, but they might leave out that word circle. So it's really important that you can tell based on the equation what shape it is, okay? So when you have an x squared plus a y squared, the number that it equals is your radius squared. That means this circle doesn't have a radius of 4, but it actually has a radius of 2. And so if we sketch a circle with a radius of 2, all right, we'll end up with something like that. And it might even be good for us to mark off right now that I'm starting at -2, 0, and I'm finishing at 2, 0, okay? As soon as I do that, I can already fill in my bounds. I know my bounds are going to be -2 to 2, because my cross sections are going to be perpendicular to the x-axis, or I'm going to be stacking them along the x-axis. Okay, remember these are just sample lines for the cross sections. It does not represent all of them. It represents a random selection of them. Okay. Now, let's go ahead. Can someone else tell me what the area formula is for a semicircle?
½ pi r squared.
Good. So over here, I'm going to go ahead and write 1/2 pi times the radius squared dx. Okay. And because I already found my bounds, I'm going to put in a -2 and a +2. Now, let's go back to this green line. Okay, so these green lines, what does that represent? Like, what part of the semicircle does that green line represent?
The diameter.
Yeah, this is the diameter of the semicircle. Okay. And I'm going to scroll back up to the top real quick so we can look back at that diagram from earlier, because it's very similar to one of the questions, or not questions, but pictures that we took a look at in the beginning. So in fact, it is very much like this picture. Okay, I have a base as a circle, and I have cross sections that are semicircles. So instead of pi r squared, I have 1/2 pi r squared. So now, if we go back to our problem number 5, okay, we know this is the diameter of the semicircle. But when I look at my equation, I don't want the diameter. I want the radius. So if I were to think about what I need, I don't need the whole green line. I need half of that green line. Okay, so the yellow part, the yellow highlighted part, that's my radius. Or this yellow part, that's my radius. Or this little one down here, that's my radius. Okay, so anything that is highlighted in the yellow represents the radius of my circle. So we're going to use the same trick we've seen before in question 3 and in question 2, where we take half of that distance, only this time we don't have to double it because it's giving us the radius, okay? So we're going to take our equation, x squared plus y squared equals 4. Now, do I want to isolate x or isolate y in this equation?
Isolate y.
Yeah, we're going to isolate y. That way our equation will have x's in it, which will match my dx, and it will match my 2 and my negative 2. So let's isolate my y. I'm going to move the x squared by subtracting it to the other side. And now I'm going to take the square root. Okay. Now, I've not done this yet today, but I've seen this, students make this mistake quite often. This is not equal to 2 minus x. I'm not simplifying it on purpose. It just doesn't simplify that way. Okay? So be aware that when you're working through these problems, not to make these algebraic mistakes that used to be small algebraic mistakes. Now they're algebraic mistakes that are going to get you entirely the wrong setup and then therefore entirely the wrong question. Okay? So don't simplify. We cannot simplify that square root unless everything is multiplied. All right? But what we have here is the equation for our radius. All right? So I'm going to bring that up to the top. So square root of 4 minus x squared. And I'm going to put that in for my r. So the integral from -2 to 2 of 1/2 pi times the square root of 4 minus x squared dx. And again, this is my radius. And so according to the equation, I need radius squared, which is why I'm squaring it. All right. Let me zoom back in for a moment. Does anybody have any questions with the setup so far? Okay. So here's what I'd like you to do, okay? We have about 10 minutes left in class. Sort of same as last time, I'd like you to finish this problem and I'd like you to email me before 12:30 with your solution, okay? So we have the setup, we have that, but I just want to make sure that we know how to integrate, simplify and integrate the expression that we have, okay? So make sure to do that before 12:30 today. But in these last few minutes, I want to take just about 5 minutes to take a look at what we're going to be starting at on Thursday, okay? As you can tell, these are like pretty gnarly problems for our brain to think about, and I want us to like at least start to think about what's going to be different, but also the same for Thursday, okay? So let me go ahead and scroll up. Okay. So next time when we meet, we're going to be learning something called the disk method, and it's also sometimes called the washer method, okay? So these are going to be a very special type of problem where all of the cross sections are going to be circles. So not a triangle, not a square, not a semicircle, not a quarter circle, but a circle, like a full circle, okay? Now, sometimes students see this word washer method. They see the word washer, and the first thing they think of is a washing machine, okay? That's not where washer comes from, although you can, from this particular type of photo, see the washer method, okay? But if you've ever assembled like a desk or a bookshelf or some kind of furniture. You have like screws and nuts and bolts, but you also have a washer, okay? And a washer is kind of like this picture right here. It's like that flat metal disc that has a hole in it, all right? So that's the washer they mean. They do not mean a washing machine, okay? So when we say a washer, we're thinking about a flat disc that has a hole in the middle, all right? And so we're gonna look at some cases where we have a hole in the middle, and we're gonna look at some cases where the hole in the middle does not exist. It's gonna be a hole of 0, okay? And so what we're gonna do with that, you can think about this maybe like the one with the hole in it is like a regular, when you imagine a donut, right? Like a donut has a hole in the middle. But I think about this one as like, I prefer donuts that have fillings in them. So like I really like a jelly donut or like a Boston cream donut. So like to me, I think about this one also as a donut, but it's just like the filled kind of donut, okay? So next time when we meet, we're gonna talk about specific situations when all of the cross sections are circles, all right? So it won't be as many different formulas to remember, like, oh, 1/2 base times height or length times width. We're gonna be using pi r squared a whole lot for these cases, okay? And somebody, I think it was Abby, asked a really good question earlier about how do we know what shape? And so no one's gonna tell you in these problems that the shape is a circle, but the way that it's worded will figure out how you know it's gonna be a circle, okay? So that's all I want to say about that. The last thing that I want to say, and there are already pictures in here, you can take a look at these before Thursday's lesson if you want to, but where is that? Ooh, so many examples. All right. So I just wanted to leave you with a little something. I know this topic is super challenging, and honestly, I'm really nervous to be teaching this remotely because I think it's just a hard topic, all right? But someone sent me a really great recipe for donuts that you can make at home in your air fryer if you happen to have an air fryer. It's like one of those new kitchen gadgets that a lot of folks have. But if you happen to have an air fryer or have a friend with an air fryer, and you can buy some of that Pillsbury biscuit dough. All right, so if you go to like I don't even know what section it is in the grocery store, it's like by the butter maybe, I don't know. But anyway, if you buy like a roll of the Pillsbury biscuit dough, you can actually make donuts in your air fryer like super, super fast. Like I think it takes like 6 minutes in mine, and it's quite delightful. And maybe that'll be, you know, a fun way that you can make yourself study or spend some time with all these different cross sections that we're talking about by enjoying a delicious snack. But anyway, I thought I would add that in there for you because I had some the other day and they were pretty delicious. So, all right. So let me go back up to the one question that I want you guys to email me before 12:30. Okay, so this was the question. I'll leave that up on the screen for just a little bit in case anybody wants to take a quick picture or screenshot so that they have the work and they can finish it and send that back to me before 12:30, okay? All right, is there anybody who still needs this photo up on the screen?
I have a quick question about this problem.
For sure, what's up?
Would you pull out the 1/2 and the pi to the other side?
Yeah, I would.
Okay, got it, thank you.
Mm-hmm. Yeah, and that's such a great question. Sometimes, like, the higher up you go in math classes, the less steps that a professor might show. So that might be a really good step that
you should get used to could be skipped. Like some people put the 1/2 pi out in the front right away, not inside.
And then you take the 2 out to make it to like a 0 to 2, right? For the bounds.
Yeah, you could go from 0 to 2 and then double whatever answer you get. Yes. All right. Any other questions on this particular problem?